Hi there. This is a test between Siglent 83, Rigol MHO98 1 GHz, the Siglent SDS. This one is a hacked version, so it's a 2504X Plus, and TinySA Plus spectrum analyzer. I'm measuring on the DC-DC buck converter, step-down converter, TPS 54531, and I was curious how the noise was in the switching regulator. The schematic is up here from the keycard, and what I'm trying to do is the 5 volts this unit gives out from my DC power supply over here is 20 volts, and the current draw is not much. It's 15 milliamps, so 0.3 watts. The load is very low on this one. Anyway, I have 3 oscilloscope probes connected to the 5 volts and the same ground. Then I have the oscilloscopes connected in AC mode on each, the Siglent, the Rigol, and the Siglent oscilloscope on channel 1. I also have the TinySA, just with I don't know what this tool is called, but just a sniffer that I'm holding just above the switching regulator. I put the different oscilloscopes in FFT mode, and maybe, yeah, here you can see everything is online at the moment. It's live, and starting from the Siglent 83, it's a 14-bit oscilloscope. It's set to it's turned all the way up, so I can turn it down and I can turn it up on the voltage scale. It's on AC, and the speed time division is ranged 409.6 microseconds per division. This signal, the 14-bit signal, is then analyzed in a spectrum FFT, and it's on, it's on peak hold continuous mode. If I just say sample, it's just noise, but putting it in the peak hold continuous mode, it holds the maximum steps. I put in some cursors where I know there is some noise. From the datasheet, it's at 570 kilohertz switching, so that's where I'm going to search, and there's a peak right there at 570 kilohertz, and then the next harmonic just hit would be at 1.17 something up here. 1. Oh, sorry, there's a just right there. There's something 1.17. So that's what I'm measuring on a 14-bit 83. if I measure it on the Siglent, which actually is only 8-bit native, but somehow they make it work in the 10-bit mode, I can analyze. And let's just make a new trigger. Oh, see if I just change this. Oh, there. Then it refreshes the FFT. That's what I was looking for. I can read out the different peaks, but I can also add a cursor here. I did that on the x-axis on the FFT, and I can see a small peak here at 500 and there, just about there, 500 and let's just see, 570 kilohertz. There it is. Yeah, somewhere it's a bit slow on the UI. And I have another peak here where the mouse is at 1.11 megahertz, and then I have also another peak up here and there. On the Rigol I did the same, having the signal and adding a FFT mode on it, and I have a very visible peak in the hold, max hold on the FFT on this signal, and I placed manual cursors as well on this one, and I can see up here on the top right corner here, I can see the frequency. If I just change the cursor one a bit, oh, it's down here. See, it should be at 570 kilohertz there, and 1.17 kilohertz is up here. There. So that's what I'm seeing with a Rigol that is native 12 bits. And the TinySA I had here with this one, with the sniffer, PCB sniffer. It's quite obvious the frequencies going on the PCB. And if I just remove the max hold, that was the purple one, this is the live signal, the green one. It analyzes the signal very well. Just a demo on spectrum analyzer, Siglent 14-bit oscilloscope on FFT, Siglent 8-bit oscilloscope, and a Rigol 12-bit oscilloscope. And this was my test setup.